Hello, this is the second section, the second chapter, the first part of the second chapter, and we are speaking about resonance. So, a resonance, let's go back to the first. Resonance is defined as the tendency of a system to vibrate with the greatest amplitude in response to the frequency that matches or comes close to its own natural resonant frequency. So, this sounds like so complex, but you'll understand it when I explain. Think about the term itself. Do you hear it in conversation? When you say, someone says something, you say, well, I can resonate. I really resonate with that. It is almost like you reflect it. They say something and then you find yourself reflecting that. You agree on what is being said, and it kind of, it agrees with you. Sometimes you also say, well, we are on the same wavelength. It means we push together, work together in the same direction. We do not oppose each other. So, first, let's go over some concepts. Natural frequency. Everything has a natural frequency. Everything has a rate of vibration that it is determined by the nature of the object. Let's take this tube, for example. Based on how long it is, based on how wide it is, how symmetrical it is, and all of that, that is gonna make it resonate at a certain frequency. Like if I say, ah, the air inside of it will respond to my sound in a certain way based on the shape, based on the length, based on the density, and all these factors. So again, every object, we do not know the resonant frequency or the natural resonant frequency of an object until we measure it using a machine. So it is determined again by length, density, tension, and stiffness. Let's take, for example, here, this tuning fork. The natural resonant frequency is determined by how tall, how long the tines are, how dense or how thick they are, and how much tension there is. Like if I see the tension that we can see here, how much tension or stiffness is there when you try to move them. So that is what we mean by the three factors that determine frequency. Now we have forced vibration. And before we do that, we demonstrate it. We have the concept of applied frequency or driving frequency before, and then we go back. So let's say this tuning fork is 320, this tuning fork is 320. However, I am gonna take this tuning fork, hit it, and then get this tuning fork next to it and put it next to it. Since they are similar, have the same frequency, now if I take the one that I hit, take it away, this tuning fork will be vibrating. I can go like this, I can hear it buzzing, even though I did not hit this one. What happened was that this tuning fork resonated, it reflected, echoed the wave that was played, that was forced, was applied to it. So this tuning fork that I hit made a frequency. And we call this the driving frequency. We call it the applied frequency. The frequency that I apply to this one so that this one can make its own frequency in response to this one. So if they are exactly the same frequency, I mean that like this is 320, this is 320, and I put them next to each other, this one that I did not hit is going to vibrate exactly, it is going to vibrate and in response to the applied frequency. So the vibration of this second fork that I did not hit, that is called forced vibration. So that is the applied vibration or applied frequency, the one that you hit directly. The second one is the forced vibration. It's the vibration of one object in response to a forced vibration by another object. So the forced vibration is the basis of resonance. So that is resonance. So resonance is a reaction, is the sound that is produced in response to an original sound. So for example, we have a guitar string. You look under the guitar string, there's a box, a wooden box. That wooden box has a certain shape, and it shapes an air column inside of it. When you pluck the guitar string, that is the applied frequency. That is the driving frequency. It causes the air inside of the guitar wooden box to vibrate in response to that vibration. So the air will produce a forced vibration based on the natural resonant or frequency of that box. Because some boxes are made to be small, they have a higher frequency, bigger, shaped in a certain way. They engineer them to have to respond in certain ways. So the forced vibration, again, in order for it to occur, the natural frequency of both objects have to match each other, or they have to come close. So if I have a tuning fork that's 320, the other tuning fork 320, if I hit this and put it next to that, I get the maximum response from this. I get the loudest resonant frequency because they match perfectly. Now, if this one, let's say, is 320, this one is 288, and I put them next to each other, this is gonna give me a tone, but it will not be perfectly as loud as the 320 hertz. The more the frequencies are different, from each other, the less the resonant response is gonna be. So they will be perfect, and it gives you the maximum amplification if for example, the guitar string matches or vibrates at exactly the same rate as the air inside of the box. That will give you, basically, that will amplify to the highest level. So, for example, I'll give you some example, like the videos that you watch when you watch the video about shattering glass. When you look at that, the glass has, glass walls. And these walls can shrink, contract, and expand. And when there's the air inside of them, if you hold the glass like this and say, ooh, as you go like that, that will vibrate the air inside of the container, inside of the wine glass. And as you continue vibrating, the air vibration will continue to be equal to, like, the glass is going to, go at the same wave. Basically, it doesn't break. Once you go to 565 hertz, you are going to produce a mismatch. Now the waves become so quick and so small that the glass cannot mimic that speed. You have a mismatch, and then these waves of the air are going to explode and push against the glass, and it will shatter the walls of the glass. So again, the closer two things are in the frequency value, the greater the response of the resonator is going to be, and the vice versa is true. So a resonator is an object that vibrates in response to another vibration. For example, like I said, there's a tuning fork, you hit it, it has an original or an applied frequency, you put another fork next to it that you did not do anything with this except for putting it close. And if they have the same frequency, natural frequency, you are going to get the maximum and the best response from this resonator. So that is called a resonator. What kind? We call it a mechanical, because you can hold it, you can feel it, it moves physically, you know, a piece moving back and forth. Please don't make the mistake, don't confuse it with the acoustic resonator. So there are two kinds of resonators again. One is mechanical, anything like a guitar string, like a rubber band, like a tuning fork, things you can touch and feel. These are mechanical resonators. Acoustic resonators are just columns of air inside of a container. This tube has air inside of it. That is an acoustic resonator. When I say ah, see, it resonates. The air resonates in response to my voice, and my voice will be the loudest it can be if the tube, the resonance of the tube matches my own resonant frequency. So if the tube again is different, too much different, like this, oh, it muffles my sound because the sound waves, the resonant frequency here is not even anywhere close to my resonant frequency. So the more different they are, the less the response will be. So resonant frequency is the frequency at which a resonator vibrates in response to the driving frequency of another resonator. An acoustic resonator, again, is a column of air, just air, vibrating in response to an original applied frequency. Like my vocal folds are going to make a tone. That's going to cause the air inside of my throat to vibrate. That air is going to be called, it will be resonance. So the closer the container's resonant frequency, RF, to the driving frequency, the greater the amplitude of the resulting resonance. So now we are going to look into resonators, resonance of a tube. Why? Because our vocal tract is a tube, but that tube is closed on one end by the vocal folds. So, but let's first look at resonance of tubes that are open on two ends. When you look here, this is open. There is no difference in pressure between the air outside and the air inside at this opening here. So that is called a node. Means there's no pressure here. This is equal to that. And the other side is the same. So it has two nodes. Now when I play a tone into this tube, that is again an area of no pressure, an area of no pressure. That my wave is going to go like this. It's going to peak in the center of the tube, will be the greatest amplitude here. The maximum point of amplitude will be in the center of the tube. So the tube, the wave is going to be like this. And, excuse me, at the first time when I say ah, the first time the air is going to vibrate, it will vibrate and only half of the wave is going to fit in this tube. Only one half. Sorry, I'm trying to show the tube. So one half of the tube is going to fit in, one half of the wave, the compression is going to fit in the first time that the air resonates. Now I made the tone and let it play. The air inside, first it's gonna make a half wave compression, and the second it's gonna replay that. But the second time it will make a full wave. That's gonna fit through the entire tube. The wave will be shorter. Remember, harmonics. First one is gonna be like twice as high as the original. So twice as high. This is half. You start with half a wave. The second time it makes a harmonic. It produces the tone, repeats it. It will be twice as long as the original. The original was half. What is twice as half? It will have one whole wave. The third time, the same column of air is going to go back into a third wave, and it will make three halves. So it will be 3 times as long as short. So half becomes 1 and then becomes 3 halves, like 1.5 waves will fit the third time. And then the fourth time, you are going to have 2 waves, 2 full waves fitting in here, because the waves will be smaller and smaller and smaller and smaller every time they continue to play. Just like the swing, the biggest wave is the biggest, the first wave is the biggest, the second is going to be cut in half, and the third will be, so it will be decreasing as you go. So resonance excuse me, of a half wave resonator, a half wave tube that is open on each end, can only fit 1/2 of the wave the first time that the air responds. And again, it has 2 nodes at either end. It has no pressure at either end. The biggest amount of pressure will be in the center of the wave, the tube. So then, again, the first time only 1/2 of that wave will fit. The second time, one whole wave will fit. Every time it repeats, it's gonna fit a half more, a half more, a half more. So now, when we speak about resonant frequency of a tube, again we said it depends on the length of the tube, the geometry of the tube. Is the tube symmetrical? Is it cylindrical? Is it bent? Whether the tube is opened or closed on one end, if it's opened on one end or both ends. Again, the definitions of the concepts: a node means an area of no pressure. In the video that you watched in class, where the area at rest, you could hold it and touch it, there is no pressure. That is rest. There's no elasticity there. And then the areas where you have the wave going like that, then the compression is there and the rarefaction is also there. An antinode is the area of the maximum point of pressure that is in an open-end tube. It is in the center of the tube. So now we look at the resonance of a closed tube resonator. A tube that is closed on one end, like the vocal tracks, closed by the vocal folds on one end and open to the lips. So you have one tube that is closed on one end. When you play a tone into a tube that's closed on one end, you are going to make, I'm trying to look for one of these containers. We can just use this. It's closed on one end, and then you play a tune, a wave here. The wave, the end, the open end, the air pressure is equal to the outside air pressure, so it has a node here. Now when I go like that, the maximum point of pressure is going to be at the closed end. that is the antinode, will be at the closed end. So when I say the first time the air vibrates inside of this tube is going to be only 1/4 of the wave is going to fit into that container. Any container that is closed on one end, only 1/4 of the wave that you put into it is going to fit the first time. So the second time the air is going to vibrate that quarter of the wave, the wave is going to be cut short because harmonics are rising frequency as you go away. So the second time you are going to have 2/4. The second wave is is gonna be 2/4, half of the wave. The third time it will be 3/4. The fourth time the air continues to vibrate, it will be 4/4. The fifth time, 5/4. And you keep going and going and going and adding, every time the wave becomes smaller and smaller and smaller, more of it will fit, more and more will fit into the tube. So, because of the quality of the air, the closed tube container, like our vocal tract, it produces standing waves. Standing waves are the ones where compression aligns perfectly against rarefaction, and the wave it creates opposing forces. At some point, like when you have 4/4, you have a complete wave, then that complete wave is going to be like this. It will not be doing much, and the vocal tract will just mute it out. And this way, a quarter wave resonator by definition is a filter. A filter means it takes out certain things and it leaves the good things that we would like to get. So in a closed wave, 1/4 wave resonator, or a closed tube that's closed on one end, you have one node, one area of maximum, lowest pressure at the opening, and the antinode is the area inside where it has the highest amount of energy, and you have an even distribution of nodes and antinodes. Now, if I know that this tube the first time can only take 1/4 of my wavelength, what do I need to figure out the length of that wave? All I need to do is to get a tape and to measure the length of this tube. If I say, this is 4 inches, that means the quarter, this is by definition will only allow 1/4 of my wave, not more, not less. So that means if 1/4 of my wave fits in the first time into 4 inches, well, I can figure out the whole wave. So I say a quarter is 4, so I have 4/4. 4 times 4 equals 16. So my wave then is going to be 16 centimeters. So again, we'll do some examples like these, but the idea is, because 1/4 of the wave will fit the first time. If you know the length of the tube, you know 1/4 of the wave, how long it is, and then you can multiply by 4 to calculate your the length of the wave. And if you get the length of the wave, you will be able to calculate the resonant frequency of the vocal tract itself. So the wavelength of the lowest resonant frequency equals 4 times the length of the tube. That's another way to say that original first wave that you play, when the air echoes inside of the container, only 1/4 fits. So that means that the wave is 4 times greater than the length of that tube. Now, the second thing is all subsequent frequencies that come after the first time that the air resonates, all the next, all the frequencies that come after that, they are odd multiples of the lowest RF. Again, that concept sounds like, oh my God, this is so complex. I'm going to explain it to make it crystal clear. So first, the wave, first the standing waves. There's also a video that shows them. And standing waves are created inside of a quarter wave resonator. This is the time when the incident wave, the wave that hits a barrier, bounces back at the same time that the original wave goes in. It causes echoes, and so the original wave comes in, and then it reflects against the barrier, the end of the tube, and then they have the other, have an exact copy of that wave made. So you have now, but it is reversed. Now you have compression aligned against rarefaction, rarefaction aligning against compression. They are pushing against each other. No, this one is not moving, that one is not moving. They are opposing forces. So again, both waves are mirror images of each other. However, the compression and rarefaction are perfectly aligned, against each other. Now, as I explained, quarter wave resonators act as filters. So in this way, they enhance the sound by deleting certain opposing forces and by leaving other forces that will make the wave nicer and more amplified. So again, an acoustic resonator amplifies frequencies that are closest to its resonant frequency, and they attenuate, means decrease, the frequencies that are farther away from the original, from the resonant frequency. So let's say this tube here has a resonant frequency of 400. Let's say that I put it on here, say, and if my frequency was 400, and I say, I will get, this will be like a microphone for me. It will enhance, it will amplify my sound the loudest it could, because I am 400, this is 400, they match perfectly. But if my frequency, let's say, is 300, this is 400, I'm gonna get some, but not as loud. If I become 200, this is 400, it will a little bit, but not as loud, it decreases. The farther away the frequencies are, the more different they are, the less the amplification. That's the idea. And what decides is the natural frequency of the object, of the tube that we play the tone in. Bandwidth. Bandwidth is a, let's see if I can get it. So bandwidth is a range, and everything has a resonant frequency, and everything has a bandwidth. Let's say this tube is 400. I'm just guessing. The bandwidth of it could be 200. How is that? That means 400, if you increase frequency, if you get a frequency that is 100 less, like say 300 hertz, and you play it in here, that is going to be amplified. If you get a tone that is 100 more on the other side, that 500, that is going to be amplified. That means the cutoff frequency is the the frequency of the object itself, I'm sorry, is called the natural frequency or the center frequency, 400. And in order to come to 400, close to 400, or within 100, 100 frequencies close to it, it can be before or it can be after, as long as the distance is for 200. So the two possibilities, when you have 400 here, and you could be 100 hertz below the 400, that will be 100 of a distance, like 300. The distance between 300 and 4 is 100. So, but the distance from 400 to 500 is also 100. So what you do is you have the thing like a pyramid. You have the center frequency here. That is where the thing natural frequency is. And to come close to it within range, you can go from either side. You can go from 300 to 400, or from 400 to 500. On either side, you are going to have 100 hertz of a difference. And then you say, okay, so together from 300 to 500, that will be your bandwidth, the range within which the tube is going to respond the best way. So the closer you come, if you come 300 and say 301, 305, the closer you come to 400, the louder the sound becomes, the louder, until you come to 400 and say, I got the maximum amplification. Once you move away, 501, 505, you start to decrease and decrease and decrease and decrease. Once you reach 500, that is 100 of a different distance. Now on the other side, now the thing doesn't respond anymore. So there are 2 points, one on the right, one on the left, that we call the cutoff points. That is the lower cutoff. 300 is the lower cutoff. 500 is the upper cutoff. Before you reach, like if there's a frequency that is 290, the thing is not going to care about it, because it said it is not within range. I can't pick it up. It doesn't come close to my own. And then when it goes to 500, it is also going to say, oh, 500 is okay, I can do it. But 550, it's going to say, no, 510, no way, because it's out of my range. So that range from 300 to 500 is the bandwidth. How do you calculate it now? You say, basically, the distance from here, 500 minus 3, that is 200. Or you can go 100 on one side, 100 on the other side. That becomes your bandwidth. And we don't know the bandwidth of everything. You just have, to calculate it. Use a machine to get you the bandwidth. So when you have questions about these, I will give you information to start with. So let's see. There is an open tube that has an RF of 500 hertz and the bandwidth of 400. What is the frequency? What frequencies will be enhanced? What frequencies will be attenuated? Let's say the open tube is, it doesn't matter to us, but what you do is you make the line and you make the center frequency here. Center frequency is 500. And then you get, the range is 400. Anything that can be amplified has to be within that range. So what you do immediately, take the bandwidth and split it in half. Here is your center frequency. the possibility that you can get close to 500, there are two possibilities. One way is to go from 300, 400, 500. One way is to go from 500 to 600, 700. So it is a pyramid. Whatever you do in the lower end is repeated on the other end. So you take that 500 and say, okay, this is the whole thing. I'm going to split it. 200 will be lower, below the 5, and that will be 300. That will be the end where no amplification will happen before that. And then on the other side, you say 500, you put 200 more. So you split that 400, put one on one side, half on one side, half on the other side. So now again, you get 300 on the lower end and 700 on the higher end. And the entire range from 300 to 700 gives you the 400 of the bandwidth. We'll do more examples in the class. So when I ask you what frequencies will be attenuated, when you make that graph and you say 300 to 700, anything in between 300 and 700 will be amplified. The closer it comes to the resonance of the tube to the 500, the louder, the most, and then the best is when it matches 500. So imagine yourself like this. You have a tube that is, say, 500 hertz. And you want to say, okay, the one whose frequency comes close to the tube is going to receive the best, to be amplified. However, the closer you are to the 500, the better the tube is going to respond to you. So someone comes in with a hoarse voice and a bad cold, and you say, oh, and the tube doesn't respond much. It gives you a little bit. But someone comes in and says, I am, closer, and you go to, 300, and the tube is going to give you some response. But someone else is going to come and say, my voice is different. My voice is 400 hertz. And say, and the tube gives you more. And someone comes and says, I can get you a perfect match, get the loudest effect. The tube is going to like me. I'm going to play 500, and the tube is going to give you the loudest sound it can give because you have matched exactly its natural resonant frequency. So someone else is going to go, I can get it to respond. I have a 600 tone. 600, it will respond. 650, 700, yes, but it will decrease as you go away from the 500. And then beyond 700, it's going to reject. It will not, give you more. So what frequencies will be attenuated or decreased? Any frequency below 300, any frequency above 700 will be attenuated. Narrowly tuned, broadly tuned resonators. This is an exam question. You always are going to have this question. So be ready, study it, know the difference between narrowly tuned and broadly tuned. Narrowly tuned resonators have a small bandwidth. For example, instead of this tube having 400, responding at 300 to 700, if it was narrowly tuned, it might be like 100 or maybe even 50 hertz. Let's say 100. So that means if it's 500 hertz, it can only respond, and it has 100 of a bandwidth, it can only respond if the tone you play is 50 less or 50 more. That gives you the 100. Because you split that 150, 50 there. So if it is 450, it will respond. As you go closer to 500, it increases. If you go 550, it will respond. Again, as you go back to 500, it will give you the best response. So that is a restricted range. That means it has a small bandwidth. A narrowly tuned resonator is going to it will warm up. It will respond slow, 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 and then it rises, builds up to a greater amplitude. And then as the sound goes away and you stop the sound, it's gonna die down slowly, 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 slowly. In other words, it gives you echoes. And when you start to speak, like in the old, if you call someone overseas who is in a country that doesn't have new phone lines or new, equipment, and you speak, you hear your own voice coming back to you. The person says something on the other end, and then there's a delay, and then you hear. So that causes a lot of confusion. You say something, the other person says something, the sound doesn't come exactly on time, and there is a lot of feedback, and it really disrupts. All of these things were narrowly tuned. They were not functioning well. You say something, it takes a while, and then by the time the person responds. For TVs, look at the old black and white. Watch the lips. Listen to the sound. You notice the lips are saying something, the sound comes later. So there's a mismatch. Now, a few years ago was broadband, everything was broadband. It means it can give you so many frequencies at the same time. It is when you watch a game, whatever happens, at the very second that it happens, you see it right as it is. There is no delay. There is no delayed feedback. There is no mismatch between lips and the voice and all of that, because it has, broader band. In addition, a broadly tuned resonator, once you play the tone, it buzzes immediately. Once the tone is done, the thing is heavily damped, it immediately stops. It doesn't give you delayed feedback. So examples of narrowly tuned resonators are cylinders. They are perfectly shaped and symmetrical, and they don't allow just any kind of, frequencies to go in. They have to be very, very close to their own to allow them to amplify them. So anything, the more symmetrical something is, the more narrowly tuned it is. The more irregular it is, the more broadly tuned it is. So things that are not regular in shape, that are not symmetrical, are going to give you a broad, band. Examples are earphones, loudspeakers. Actually, this is an error. It's not the tympanic membrane. I apologize. It is the ear canal. The ear canal is a broadly tuned resonator. The tympanic membrane, not the tympanic membrane. The vocal tract itself is a broadly tuned resonator. So, bandwidth and the cutoff frequencies. We said the cutoff frequencies are the frequencies beyond which the tube doesn't respond. So let me show you something and come back again here. So here is an example. You see that dotted line here? That is the line where if I go to between this line and the center frequency, everything is amplified. And from between the center frequency and the other dotted line here, everything is amplified. That is the bandwidth. Beyond, on the left side of this dotted line, then now you have the cutoff point where once it reaches that, the tone is attenuated very, very quickly. It starts to be decreased and rejected. The same exact scenario happens on the other end beyond the upper cutoff. So the lower, on the left side, that is the lower cutoff point before which the tube doesn't respond. And on the other side, because it's the higher frequency side, that is the upper cutoff point. And beyond that point, the tube doesn't respond. It starts to reject. And it is here that is called sometimes the -3 decibel, or the dupe, has a where is it? The 3 decibel down point, or the cutoff frequency. So there are two of them, one on the left, one on the right, because what happens on the left exactly is similar to what happens on the right. That is the point. The 3 decibel dew point is also the point where the frequency reaches 70.7% in loudness of the center frequency. Beyond that, then the signal will start to deteriorate and will be rejected after that. What is a resonance curve? It's a curve that depicts how resonance is. It has the center frequency on one in the center, and on the left side it has the lower frequencies. On the right side you have the higher frequencies, and you end up having that bell curve. What happens on the left is exactly similar to what happens on the right. So it shows, a resonant curve shows a resonant frequency, it shows the center frequency, it shows the lower cutoff, the lower frequencies like 300 to going to 5, and the upper cutoff, which is passed on the right side of the center frequency. And then it shows you now the distance between the lower cutoff and the upper cutoff. That distance is your bandwidth. So that resonance curve, it shows you the bandwidth. And it also shows you the attenuation rate and the rejection rate. You know, below, for example, below 300 is not going to be attenuated. Above 700, for example, in the example I gave you, it's not going to be, it will be attenuated. And you go to figure 2.7 on page 55 to understand more. There are 4 types of filters. And we said the filter is, a tube that selectively takes out opposing forces and leaves for, enhances what is left. There's a low pass filter. Low pass means it allows the low frequencies, any low frequencies. It allows frequencies below the lower cutoff. And it rejects frequencies that are above the cutoff. So for example here, let me go here. Here, for example, there at this point here, there's an upper cutoff. At some point, you should have a lower cutoff here, but because this is a low pass filter, it lifts up, it makes any tone that is below, that's on the lower end, it makes it amplified. And then it makes the right side, which is the higher upper cutoff, if it reaches a certain point, actually here, it's going to reject, that afterwards. So again, low pass means it allows the low frequencies below the cutoff to pass through, to be amplified. High pass. High pass means if you take this and make the low end here, make this here like that, and put the cutoff here, and lift this away, make it like on the left, that would allow the high frequency sounds above the high cutoff. So it's the opposite, exact opposite of the low pass filter. Then we have the band pass filter. Band pass, band means bandwidth. So it takes the width that is allowed, the bandwidth of the tube, and anything that is beyond it on the left or right is completely shut down, and anything that is within that bandwidth is completely amplified. So you get this here, then that whole bandwidth in between this and that is amplified, enhanced, and anything below on the left or right is shut down, is basically rejected. Then you have the band stop filter. The band stop is the opposite. If you want to muffle a sound, or we use it for hearing testing in certain cases. The band stop means it takes the bandwidth and mutes it. It will be inverted down like this, and it mutes it, and then it allows, on the left, it allows what is below the lower cutoff, and it allows what is above the upper cutoff. So that is the band stop is the total opposite of the bandwidth. It is, they use it to muffle certain sounds and just take a word and just take certain sounds out of it to make it muffled for speech purposes. So again, I'd like you to know these 4 kinds of filters, and there are examples in your textbook. So we will follow up with the next section, and hopefully it will be available tomorrow at some point before noon. Thank you.